students, in this video we will see graphical representation of the equilibrium situation. Okay. First of all, this is the general situation. This is general equation. But to understand how to represent it graphically, the equilibrium situation, we should know the law of mass action. Definition. What it says, at a given temperature, that is when temperature is kept constant, the rate of a reaction is directly proportional to molar concentrations of reactants. Is it clear, students? Rate is directly proportional to concentration. Simply remember this. Rate or speed, or you can also call it as velocity of a chemical reaction is directly proportional to concentration only or substances. Concentration of substances. This substance can be either reactant or product. Remember this. This is very much important. Rate of the reaction directly proportional to concentration of the substances. That substance can be a reactant or product. Well, if you are dealing with the forward reaction, we use for forward reaction we use reactant, and for backward reaction we use products. Okay, students? Okay. It means that if it is increasing, it will increase, or if it is decreasing, it will decrease. Okay, students? Okay. Now we write the graph. See, this is one axis, this is another axis. Here we take concentration, and here we take time axis. This is 0. Now we deal with reactants, concentration of reactants, which is usually expressed in terms of mole per liter. Initially means this is initially means time t is equal to 0. That means here initially quantity of the substance will be always more. Let us say this is the concentration of substances, reactant. That's what I mean. This is initial concentration of reactant. Now reaction is started. Then what happens? Some quantity of the products, some quantity of the reactants slowly get converted into products. It means as time progresses, concentration of reactant decreases. Yes, students? That means we can write like this. And a stage will come where concentration of reactant will be fixed. It will remain unchanged. It will remain as it is. That situation where concentration of the reactant is not changing, that situation is called as equilibrium situation. See, this is the reactants behavior. And how about the products? Initially, products will be 0. Right, students? Initially, product will be at 0 level. No product is forward. That means before starting the reaction, there is no question of having the products. That means concentration of product will be 0. As a reactant decreases, concentration of reactant decreases, concentration of product will increase. That means a stage will see here. It will be the behavior of the product. And a stage will come where concentration of product will also remain same. It means that, see here, at this situation, as time progresses, concentration of reactant and concentration of product is not changing. Therefore, this situation is called as equilibrium. Is it clear, students? This situation is called as equilibrium. Well, what is this then? What is this? Here, concentration of reactants and products both will be found equal, but it is not stationary, it's not stable. This is the stable situation. Stable. For equilibrium, this stable nature is must condition. This is unstable. That means it will change immediately. As time progresses, it will change immediately. See, therefore, here this is for a short period of time. We may notice that concentration of reactant is equal to concentration of product. That's all. It will not, it's of no importance here. Simply we can say that, yeah, this at this particular time, concentration of both reactants and products are equal. It doesn't mean that it is at equilibrium. Equilibrium is this one. Is that clear, students? Okay. Now, if this is to be done here, and this is to be represented in this form, see here, these are the reactants and these are the products. It means that this will be A plus B and this will be C plus D. Is it clear? That means molar concentration of C and D, molar concentration of A and B are not changing at this stage. So whatever reactant is left, it is remaining as it is. Whatever concentration of product is formed, that is also fixed. This is formed, produced. This is remaining, left. So both are found to be equal. At this situation only we call it as equilibrium situation. Now, the same can be applied even for this. See here, in place of C and D, what is there? HI is there. It is not necessary to write the stoichiometric ratio. This is HI. That means concentration of HI is fixed. And here, H2 and I2. Concentration of these two put together is fixed. Is it clear, students? So all these situations can be written in only one graph. It means that equation may be anything, equilibrium may be anything, but their behavior is same. That means if it is concentration of reactant versus time graph, then if it is the initial time, then concentration of reactant is highest. Then as time progresses, concentration of the reactant decreases and attains a minimum value, a certain value. Then if it is the graph of concentration of product versus time, then if this is the initial time, it is the concentration of the product initially. Then slowly as time progresses, this will be increasing. That means this situation where the concentration of the product is not changing, this is called as equilibrium situation. And this is the case where concentration of reactant is remaining same. That means this situation is called as equilibrium. So both are combined in this.